Hey guys, your boy Chili here, coming back at you with some coding problems from the interview preparation kit on hackerrank.com. Last time we looked at this minimum swaps one, kind of like a sorting problem, I guess. I don't know. It was not particularly difficult. Let's take a look at something else. Let's take a look at something outside of the array section. So we'll look at dictionaries and hash maps. So what have we got here? We got a bunch of medium ones here. Easy. We're not going to be looking at these easy boys. Sherlock and anagrams. Sounds good to me. What do we got here? Two strings are anagrams. Yeah, I understand what an anagram is. You can rearrange the letters of one string to form the other string. So Alright, so what are we talking about here? I lost up. Given a string, find the number of pairs of substrings of the string that are anagrams of each other. So we want all the pairs that are anagrams of each other. Alright. So what does that mean here? Well, this M and this M are both different substrings of the string, and they're both anagrams of each other, right? Because M, you rearrange M and it is M. Yes. And then we have MO is one substring. I can't select this text. It's very annoying. MO is a substring and OM is another substring, and you can rearrange those and they form the same string. So those are two pairs of substrings. Fair enough. And we want to find all such pairs given a string. Now, the important thing to look at here, so the problem will have Q strings, and each of those strings, the length will be from 2 to 100. So that's a fairly short, our n is basically the length of our string. That's a fairly small n, and that indicates to me that this problem might be requiring an n squared. We could probably solve it with an n squared. I don't know if that would be the optimum strategy, but it would definitely be a strategy that allows us to pass the test cases. So I'm definitely looking at like an n squared thing here. Now, like I said, from the problem constraints, I'm already eyeballing a n squared solution, and that's a good fit for substrings because we can generate, or we can examine all substrings with a nested loop. And nested loops, that's the hallmark of n squared, right? So it all fits. I know all the pieces fit. That's what I'm trying to say here. So we'd have two loops, outer loop, inner loop. Iterator of the inner loop starts at where the outer loop is. And so then we iterate, here, we examine this substring. Here, stop it, give me my thing. Here, examine this substring. Examine this substring until the inner iterator reaches the end. And then we would advance the outer iterator. And then in the inner iterator, we'd start here. We would examine, starting from here to here. And you keep doing that, and you would end up examining every single possible substring. So what are we going to do with these substrings? How are we going to figure out how we're going to count pairs of ones that form anagrams? Well, we make a simple observation. If I have two strings, let's say SSO, SOS. If I sort these strings, we get OSS, and if I sort this one, we get OSS. So, two strings that are anagrams, if you sort them, they will compare equal. They will become the same string. So what we're going to do, a very simple way to solve this problem, is for every substring, we're just going to sort that string, and then we are going to insert it into a map. So our map is going to be, substring maps to count. How many times have we, that's not how you spell that, but how many times have we encountered that substring? So we can just sort a string, insert it into the map, and it's gonna be good. Now, this probably isn't going to be the optimal solution, but it will be enough to pass the conditions, and that's mostly what I'm interested in. I'll discuss a more optimal implementation afterwards. So for this anagram thing, we're gonna need a map. And I'm going to encapsulate our special map that maps anagrams to each other and counts them. We'll put that in a class. We'll call it the Anagram Map. All right, fair enough. Put my semicolon there because it doesn't do it for me. Public interface. So what are we going to have? Well, we're going to have a function to push a substring into the map, string S. Let's just mark it no accept because what the hey? Why not? And first thing we're going to do is we're going to sort our string S. And then we are going to emplace that into the map. Now, emplace returns a pair. Map.emplace returns a pair, which gives you an iterator and a flag telling whether a thing was inserted or whether it already existed in the map. So we're going to std move our string, and we're going to emplace it with the value of 1. I guess I should probably tell you what the map is. Private. So what is our map? Well, that is just going to be an unordered map. String to int. The int is the count, the number of substrings that match this anagram pattern. So that's our map. Let's unindent that. So we're going to get this return value R. Make it const because that's what I like to do. Now if not r.second. R.second is a boolean telling us whether the thing was actually inserted or whether it pre-existed. And if it pre-existed, then r.first is the iterator. That gives us a pair of elements in the map, string int. So r.first is our thing, second is the count, and we want to increment the count. So we try to insert into the map with a count of 1. If that is inserted, that's a new anagram pattern, then we don't do this. But if it didn't insert, if it already existed, we want to increment the count at that pattern. Now the second function we want to add here is we want to be able to count all of the anagrammatic pairs. Const no except. So how are we going to do that? Well, let's use some magic. Return accumulate. So we're going to run over our container. Map is just a container. You can iterate over it. Begin map.end. And our start value for accumulation is going to be 0. And yeah, let's just add up all those counts. And then that should be the count of our pairs, right? Wink, wink. Let's now implement the top level of this thing here. So what are we going to be doing here? Well, we're going to create anagram map. We'll call that our map. And then we're going to iterate. We're going to have our 2 nested loops. So for auto I is equal to s.begin, as long as I is less than s.end, plus plus I. Inner loop for auto j is equal to I, as long as j less than s.end, plus plus j. What are we going to do here? Well, now our substring is just the string between I and j plus 1. So we're going to map.push, create a new string using iterators I and j plus 1. There you go. This will push into the unordered map. The unordered map will sort, check to see if it already exists, do its thing, count them all up. So at the end, we just want to return map.count. There you go. Problem solved. Not too complicated, right? Only it probably won't work, right? You think it'll work? I don't think so. But let's see if it compiles first of all, if I haven't done any syntax errors. Compilation error. So my syntax is not correct here. What is the problem? Right. So I'm trying to use the algorithm to accumulate elements of this container. But the elements of this container here, let me see if I can find it here. The elements of the container aren't integers, right? It's a pair, string int pair. And how do you add two pairs together? It's not really defined, is it? So we need a specialized operation for that. Simple enough. Do auto. All right, now I always I get the binary operation, I always get it messed up. Is the first one the carry or is the second one the carry? All right, the first one, I believe it's the first one that's the carry. So we'll call this one the accumulator. Second one, I'm going to call that the, what do we call it? The value? Sure. V. And what we want to do, well, I think accumulator will just be int. So it doesn't make any sense to make it a reference, but whatever. It doesn't matter either way. What matters is that we return acc plus v dot second. There you go. Second is the count. So now it'll be summing up all those counts. This should work properly, right? Wink. Winkety wink wink. At least I hope it compiles. Okay, it compiled. And we get the wrong answer every time. And you see why. Well, I mean, it seems pretty clear here. Here we're counting the number of distinct anagrammatic signatures, basically. But we have to count the pairs of matching anagrams. Like, for example, look at this one here. A, B, C, D. It has many distinct signatures. You know, A, B, C, D are all distinct. And then A, B and A, B, C, B, C. So if we count those all up, that's 10. But how many actually match? Well, look at the anagram A. It doesn't match anything else because there's no other A's in the string. And same for B, same for C, same for D. In fact, there are no matching anagram substrings. That's why the answer expected is 0. But we're getting 10 because we're just counting the number of signatures. So we have to count the number of pairs. And you might say, well, that's simple, Chili. We'll just we'll check to see if this count is greater than 0. And if so, we'll add that in or something like that. And that way, if there's only one, it won't count. But that's not good. The way it works, so if there's only one signature, that means there's no pairs, right? If there are two signatures, that's one pair. If there are three signatures, that's three pairs. If there are four signatures, that is 1, 2, 3, 4, 5, 6 pairs. If there are 5 signatures, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs. Get what I'm saying? So it's not a simple, not a very simple relationship. What is the relationship? Well, how do you form pairs here? You form pairs if you have n items. You form pairs by having n and taking combinations of 2 of them. How many ways can you make those combinations? That is how many of these you have. So NC2. What is the formula for NC2? Well, in general, the formula for NCR, N and R kind of look similar if you think about it. That's N factorial over R factorial times N minus R factorial. Now, in our case, R is equal to 2. So it's N factorial over 2 factorial, which is just 2, times N minus 2 factorial. Now, if we expand out N factorial, we know that N factorial is N times N minus 1 times N minus 2 times N minus 3, minus 4, minus 5, whatever. But we can just say N minus 2 factorial is N minus 2 times N minus 3 times N minus 4, etc. So expand that. 2 factorial is just 2, and then n minus 2 factorial. Well, n minus 2 factorial divided by n minus 2 factorial is just, they cancel out, right? And so the end result, this is how many combinations you have taking 2 pairwise. N times n minus 1 divided by 2. So if we have n anagram signatures, this is the number of pairs that we can make with them. So we're going to return accumulator v.second, which is our n, times v.second minus 1. And then, let me see here, we divide that by 2. How's that? How do you like that? Why are you under squiggling me? Yeah, this lines up. This lines up. No, okay. You're just having a brain fart. Fair enough. So this seems to be good for me. Let's run the code again and see if it's green. It is green. Okay. Now the moment of truth. Does it pass the tests? And more importantly, does it time out on any of them? And it doesn't time out. So the n of, 100. Yay! We've earned our star. The n of 100 here. Yeah, 100. That was small enough to allow for our solution. Question is, well, what is the time complexity of our solution? Well, we know from the, where is it? From the outer loop here, from this nested loop, this is n squared right here. So this is n squared times the complexity of adding one thing into our map. Well, okay. So putting something into an unordered map is big O of 1, generally. It's constant time complexity. So that's just n squared. However, whenever we insert a string into here, we have to sort it. And the length of that string is generally dependent on the length of the input string. So this is going to be n log n. So we have n squared times n log n. That's n cubed log n. That's not a very good time complexity. It made for a very easy solution and it passed, so I'm happy with it. But could we do better? Yes. We could just change the way we encode our signatures for anagrams. We can note that if we count, let's create an array here, and the dimension's 26. So each one of these elements corresponds to a letter of the alphabet. And we can count in these buckets here, we can count how many A's. So we have, for this one, OSS. Let's say, so we have one O and then like 2 S's, right? So strings are going to be anagrams of each other if the counts of their letters are the same. So instead of encoding our anagram signatures as a sorted string, which has a maximum length of n, we can encode them as this bucket, which has a maximum length of 26. Much better, especially if you make your n a lot bigger than 100. Okay, so that's part 1. Now part 2, the big problem here is that we have to sort this string of length n. Now what we could do with this bucket is instead of sorting a string, we could just build the bucket for every substring. And that would be complexity of n, right? For every substring, which has a length on the order of n, we would just scan through all of those and count the letters. So that's big O of n. That would bring us from n cubed log n to just big O of n cubed. But we could do better than that still. So, and here's where the trick would come in. What we would do is in the inner loop here, we're always growing by just one character. So the counts of this substring here, they would just remain. And if, let's say the next letter is an S, we would just increment the S. every time we grew. So we don't have to scan through the entire substring every time and count all the letters. We just have to look at the one that was added and update the existing count. So now, for every substring, for every inner loop operation, that's just big O of 1. So we've gone from n cubed log n to n cubed to now n squared. So we can do this in n squared, which is obviously much better than n cubed log n. I'm not gonna, because we've already solved the problem, but I mean, the idea is there. We could do it if we wanted to. And if you want to, go right ahead. All right, so I know that I said I wasn't gonna go over the n squared solution, but you know, it's Alton Brown. You know I had to do it to him. So let's do this thing. N squared. We're gonna be hashing up our signature as a letter count instead of as a sorted string. So we're gonna need to do some manual hashing. We're gonna want a function to combine, components, hash them together to create a single combined hash. So we need a function for that. And I mean, you can make one yourself. You could do something like just add the values together. That's a terrible hash. That's cryptographically, it's not good. It's going to create more collisions in general. So I just Google hash combining function in C++, and it takes me to a Stack Overflow answer, which has this function in it. And this function is from the Boost library. And, does some bitwise logic, a little bit of adding, a little bit of shifting, and Bob's your uncle. So we're going to be using this hash combiner here. Now, we're going to need to represent our signatures. They're now not going to be a string. It's going to be its own type. So let's create that. Let's go class signature. And signature private. What's the data going to be? Well, it's going to be an array. It's going to be an array of cars. How many of them? How many characters are there in the alphabet? There are 26 letters in the alphabet. And we'll just call this one the counts. Public. So what's our public interface? That's not how you spell that. Close. Very close. Phonetically, you could get away with it, but C++ ain't about that. It's phonetic life. Let's create a function here, void push. So when we push a character onto the signature, what are we going to do? Well, we're going to go into the counts at C minus A, right? Because the letter A should be index 0 into this array. So we gotta do that ASCII offset stuff, and we just want to increment that boy, and that's it. You add a character to the signature, and there you go. What other operations do we want to support? Well, if we're going to put this thing into a hash table, it needs to support comparison. So let's do an operator equals const signature right hand side, and this function will not mutate the object, so we can mark it as const. And what are we going to do? Well, if this were a dumb C array, we would have to loop through basically all the indexes 0 to 25 and then compare the array in right hand side with the array in the current object, those count arrays. But because this is an array from the standard library, we can just do return counts is equal to rhs.counts, and there you go, you're done. That's the beauty of using this standard library array versus a naked array. That's one of the beauties. There are many, but that's one of them. Now we want a function here to hash our signature. How are we going to do that? Well, let's create size t hash temporary. We'll set it up as equal to 0. And for all the values in counts, for all those counts, those character frequencies, we are going to hash combine. That's that function we pasted up above into our hash, the value v. So that'll hash v, and then it'll combine it into this accumulated hash value. And then when we're done, we're just going to return the accumulated hash. So there we go. We have, why are you angry? Well, I mean, const, first of all. That's sorted. Okay. So this is our signature. This is what we're going to use in place of what we're using right now, which is this string. We're just putting a string into our anagram map. So an unordered map string, turn this into unordered map signature. Now here's the thing. When you create an unordered map, you give it the key type and the value type. There are other parameters in here. The next parameter, I believe, I could be wrong, but I believe it is the hashing function used to hash the key. Now, by default, it will use the hash function from the standard library, but that only works for certain basic types and things like string. Our custom type doesn't have an overload for that, doesn't have a specialization. Here's the thing though. Normally, you're not allowed to put things into the standard library namespace, but for hash, it's a special case. You can inject template specializations for hash into the standard library namespace. I've probably shown this in a video at some point, but let's do it here. You don't have to do it like this. You could just pass the function in as a parameter here. We'd have to make this into a free function somehow, but it's possible. However, instead, we're going to inject hash directly into the standard library to make our code down here a little sexier. And just for me to show it off. So we're going to do template specialization. So template struct hash. That should be lowercase because we're doing standard library stuff. So we want to specialize for signature. And our struct here, we're going to need a semicolon. We want to implement the operator. So let's do size t operator. And it's going to take a const signature, call it S. Const doesn't modify the object. The object doesn't have any data to modify, but whatever. And we're just going to return s.hash. So this is just wrapping around the member function hash. But now it's injected into the namespace. So now unordered map can find that hashing function and use it by default on the signature. All right. So how does anagram map change now that we're inserting signatures instead of inserting strings? Well, we don't have to sort the input string. In fact, we're not going to take a string at all. We're going to take const signature, take off every sig. And what are we going to do here? Well, we want to put that into the map. So first of all, we don't have to move. This doesn't have any kind of resource that can be pilfered, right? And this is just a plain old data composite array. It's embedded directly in the object. So we can just put sig into the map as is, and it should work. So I'll make this sig. And the rest is the same. We put this signature into the map, it will automatically hash it. And if it already existed, it'll increment the count. Now the function count down here, no change necessary, right? If you think about it, because it only deals with the counts. It doesn't deal with the signatures or whatever, the key type. It only deals with the value type in this function here, so we can leave it the way it is. So that's it. We've changed our components. We've added a component. We've changed this component. Now we've just got to change the actual algorithm to use our new system here. So this is the same. We're going to keep our anagram map here. Down here, for this inner loop, where we're growing the internal substring here. This loop keeps track of the start position. This loop here keeps track of the end position of the string. So as we're growing the substring for any given start, we're going to create a signature. Again, we'll call it sig. And for every substring that we create here, we are just going to go sig.push. And we're going to push that character into the signature. And then we do map.push, and we push that signature into the map. So as the substring grows, every different substring's gonna have a different signature, but it's built onto the signature of the previous one. So we can just maintain this one signature throughout this one iteration of the outside loop. And we just keep pushing back references, and it gets copied when it's inserted into the data structure. And then we call count, and we're done. So that's perfect. Might work on the first run. All right, so it compiled. but it didn't work. Now, here's my question to you. What's the problem? This is a little bit of a puzzle here. If you haven't been coding along, maybe you could stop the video at this point, because it's an interesting problem. It's something you could run into in real life here. What is wrong with this code? Where is things going wrong? Because I'm going to tell you right now, it's one very small thing. I've put it in here on purpose. And yeah, so if you're interested, I suggest you pause the video, code this up yourself, and then maybe try to figure out what went wrong. But I'm going to tell you right now, spoiler alert, the problem is right here. So when you create something like an array like this, whether it's just a basic C array or it's a std array, the values aren't going to be initialized. They're not going to be 0 initialized, at least not if it's an int. If it were a string or something like that, it would be initialized. But for plain old data types like int, whatever in there is just what was in the memory when you created this object. So if you want to 0 initialize all the elements, very easy. You can initialize it with just the curly braces like this, and that will make sure that they all get 0. So what it was these counts, they started off with garbage values, probably negative values, and that was screwing over all these test cases. But if I 0 initialize all the members of the counts array, then we should see green, and we indeed do see green. A beautiful thing. And if I run this code, it is going to work. Yeah. Okay. So again, I mean, I explained the time complexity, but let's go over it now that we have the code in front of us and verify that we have the time complexity that we expected. So we're looking at it here. We got this outside loop. It's looping through all the elements. That's n, right? Then inside loop. That's also, it depends on the outside loop, but the outside loop, which depends on n, so this also depends on n. And since it's nested, this is going to be n squared. So at this point, you're already at n squared, at least. Then we have 2 operations. Push a signature. What does that do? Well, it pushes a single character into the signature data structure, and that's as constant time as you can get. It just increments a single car. So this is constant time. So at this point, we're still at n squared. And then we push that signature into the map. And by pushing that signature into the map, what we're going to do, we're going to place that thing, which is going to hash the signature, put it in there. And you might be saying, well, chilly, but hashing the signature, we got another loop in here. So aren't you at n cubed? Well, no. The loop runs over a data structure that has a fixed size, which means that the operation is constant time. It doesn't depend on how big your n input is. It's always going to run 26 iterations of this loop, and therefore hashing operation is constant time. So the insertion into the unordered map is constant time. So push is constant time. So we've got 2 constant time operations in this loop here, which means that we're running at n squared. And there you go. And just for a little bit of a cherry on top here, if you look at the editorial, the solution that the problem setter came up with, we see that they were running at a s cube time complexity, n cubed basically. So we beat them by an order of n, which is pretty big. If n is 1,000,000, then our solution will be 1,000,000 times faster than theirs was. Not too shabby. As always, I hope you enjoyed this video. I hope you learned something. If you did, please click the like button. Helps a lot. And I will see you soon with some more coding problems.